Okay, today is lecture 9, which is on water treatments. And we'll discuss the first thing about how do you design water treatment system. But if you see where we are now in our syllabus, we have all the fundamentals covered, and we also learn about contamination in surface water as well as groundwater. But most of the time, as I said, the main goal of this environmental science or engineering is to minimize exposure to contaminants, keeps us healthy. But it is a fact that most of the water that we receive are not clean enough to drink. So that means you have to find a way to clean those water before we drink. So this week class is all about focused on how to make our drinking water clean. So what kind of treatments we need to have for it to make it ready. And again, I just want to emphasize everything that is covered in this class this week is part of the midterms. Anything that we'll cover from next week will not be part of the midterms, even though midterms is on week 7. So week 6 is not part of the midterms. And if you think of what is the quiz, because we have quiz also, so this is part of the quiz, quiz 2, which is on week 6. Okay, so everything that we cover this week is not part of the quiz, so that you have time to actually read and understand. And I also release the homework solutions for homework 2 and 3 this week. That way you will be able to see those for your preparation for quiz. An announcement, just to, again, I wrote in the tag window. So homework 4 is, it says D1 Friday. I thought I extended. Oh no, actually that's right. I extended the grace period on Monday. What that means is you will be able to submit, even though it's due, but it doesn't really matter if you submit later. So this is a grace period until Monday. Monday means anytime Sunday night. Again, if you delayed until Monday, I'm not going to judge you for that. So this week is you have flexibilities. If you are going through difficult time for elections or anything, again, just let me know. Just submit when you can. Okay. And obviously not after Monday. Okay, so this I extend that time to grace period in on Monday on grade scope. So that means you will be able to submit, and I'm not going to look at the with submitting late. Again, this is related to homeworks. Homework 4 is on lecture 7 and 8. I should be able to answer those. We have office hours, we have discussion sessions, ask those questions. Homework 5 will be released on Wednesday, even though it will be due on later next week. The reason I want to release it early is because this is part of the homework. This is the part of the midterms. So up to homework 5 will be part of midterm. So I want to give you guys advanced time to work on it. That's the last homework that will be on before the midterms. Okay. And quiz 2 next week. That's again based on lecture 5 to 8. So that's the week 3 and 4. Again, today's class will cover the chapter 6, which is water quality control. I uploaded the PDF. So the page that you wanted to read is section page 283 to 315. That's for entire this week class, this week of class, not just today's class. Okay. All right. So learning objective. But before that, any questions about homeworks or any midterms or quiz? All right. So learning objective, again, we'll have some quiz, practice quiz for you on groundwater, which is we covered on last Wednesday. So I wanted to just see if you have read about it, if you understand it or not. This is also a learning assessment for you, a learning assessment for you, and also a teaching assessment for me. That way I evaluate whether I cover the topics well enough or if I need to do anything. This also helps the TA to prepare their discussion materials if needed. Um, that's a few questions we'll have shortly, but just for learning objective of today's class, we'll learn about Safe Drinking Water Act, the act that enable all the water distribution company to keep our water safe. So you learn about what are those standards. And you'll also learn about the principle of drinking water treatment units. These pictures that shows here, as you see, there are water source, and it is extracted from surface water or groundwater. Then it has to go through some treatments before it can be reused or redistributed. So you learn the principle, and there are multiple process you learn, some physical process, some chemical process. So in this class you'll learn about two or three processes, or actually four processes. Number one, sedimentations. Sedimentation is all about settling particulates, large particulates, by gravity. So it is related to clarifier design. You'll see a clarifier, so it's over here. That's sedimentations. Then you'll also learn a little bit about coagulation fluctuations. You'll learn what that means. Essentially, it all means that very fine particles that you cannot filter or remove by sedimentations, you'll remove by coagulations and fluctuations. We'll talk about that. And for filtration, this is filtration. You learn about what makes the filtration efficient and how to increase efficiency. This is basically a little bit about design. And at the end you'll learn about disinfections, because at the end, before you supply the water, you have to make sure there is no pathogens. That's the last check you'll do. So you learn about that disinfection rate. You learn this rate calculation before first order decay, so if already you know this one, we'll just learn in the design aspect of it, because you already know the fundamental or mass balance aspect. So these are our learning objective of today's class. And for now, let's have generic quiz session, which is again for you to practice. Also learn about whether this is something you learned last class or not. So this is something I'll have every class, which give you opportunity to assess yourself. Okay, so I'm going to launch this quiz. The question is, Darcy's velocity is higher than seepage or actual water velocity. Is this a true statement or false statement? You have 45 more seconds to answer, but it should be easy questions if you have read it. If you don't, then it's a good assessment for you to go back and read those slides. Again, these are not graded. This is just for your assessment. I don't really check who is giving the right or wrong answer. This is all about me looking at how much percentage got it right. Um, that way I can see whether I have explained it well or not. No, is there any confusion? You have 10 more seconds. Okay, I'm going to close in 3 seconds. All right, end poll. I'm going to share the results. 63%, 63% says yes, it's true. And then 37% says this is false. So the statement was Darcy's velocity is higher than seepage velocity. If you know what is Darcy's velocity is, velocity of Darcy's, that's Q over dH dl area. And if you think of what is the seepage velocity, that's basically the water velocity, actual water velocity. That's its velocity by porosity. Okay, and porosity is always less than 1. Okay, so that means uh, this velocity would be always greater than Darcy's velocity. So that means Darcy's velocity has to be smaller than the seepage velocity. So that's the right statement is false. Okay, so let's look at the next one. Okay,
So the previous answer would be false, you said?
yes.
Okay.
Okay, the question is, which of the following factors would not directly affect the retardation factor? I didn't write the equation for retardation factors. That's something I expect you to check or read before. So you have to guess, okay, based on concept. Think of retardation factor of a unorganic pollutants. Does it allow you to change the answers or it doesn't once you answer it?
Not after you submit it.
Oh, I see. Okay, okay, I see. That's okay. So let me write the retardation factor equations. So that's 1 plus bulk density time KOC FOC, which is this so whole thing is KD divided by porosity. Okay, so I'm going to end the poll. I'm going to share the results. So as you see, retardation factor, which is the velocity of water divided by velocity of contaminants. Okay, so that depends on contaminant properties, because contaminant properties says what is the affinity of contaminants to organic carbon. So this is KOC. So that's KOC here. And fraction of organic carbon, that's already written here, because if you have more organic, it will attach to the contaminant. So retardation factor would increase. Bulk density, that's the D1. If you see bulk density is here. The only thing that you see over here, it doesn't say anything about hydraulic head. Hydraulic head affects the water velocity, but if water move faster, contaminant also proportionally would move faster. So it affects both similar ways. So that's why there is no term here directly. So the right answer would be C. Hydraulic or the retardation factor is independent of hydraulic head, because you see that equation doesn't have also that factors. So hydraulic head is H. Okay, so that's here dH over dL. That's the term. Okay, so I'll. Oh, I didn't write it who answered it. So 54% answer this one, 21% answer this, 12% answer this, and 12% answer this. Okay, so the correct answer is C. Anything I cross or the circle it, that's the right answers for your reference. All right, the last quiz. If you want to increase the capture zone width, which of the following factor would you like to change? So capture zone is basically this. Okay, so you have a well here, groundwater is moving this directions. So what it's saying is everything that comes within this line would be captured. So this is the capture zone width. Okay, it will become, so that width would be 2y. So you can, a lot of times, if you don't have to have equation, you can conceptually think to answer this. I'm going to close the poll in 10 seconds. So again, whatever comes to your mind, just answer it. Again, this is not a right or wrong answer type things here, because I'm just looking for what instinct you have when you see the questions. Okay, I'm going to close in 5 seconds. All right, so let's see. So sharing the results. Um, it says, so let me write the answer first. 20% here, 16% gives this one, 63 says this percentage, 1% chose D, accidentally provided. That's 1% just accidentally click on D. Okay, so a question was, if you want to increase the capture zone, so basically you want to influence as much water you can drag. So think of this way: if imagine you are like you have a straw and you are trying to pull water, and the higher the pulling rate, that's basically flow rate. So how, and you have in a glass of water or a container with lots of things floating around, And then if you push, you are trying to see how much you can sock in, So basically, as fast as you can sock in, the more the width becomes. So increase in pumping rate would definitely increase the capture zone width. Basically, it will increase more and more. Decrease the pumping rate. If you shock less, obviously the amount of water surface you'll influence will be less. So this can be. And then increase the pumping well diameters. If you see the equation, it doesn't really change much. Pumping rate is about basically if you apply more force, that's what it is. So that doesn't have that in the equation. So the right answer is A. Okay, so I hope this give you some idea about where you have as far as understanding. Please go back and read the reading assignments or the book chapters that I uploaded, and also check the homework question. Once you see the homework question, solve it, you'll also have improved understanding. So it's okay.
What's the formula for this?
So there's a formula. So that's
Yeah.
Q over 2B V. That's the width. Okay. So Q is flow rate. And there is a term with the angle 1 plus, I think 1 plus or minus. I have to check. Forget about this angle, but this is the maximum width. Okay. And so that means this B is the width of the aquifer, V is the velocity of groundwater. That's its velocity. So that's its velocity. And this is the pumping rate. Okay. Right. Okay. So you can check all that. Any question? All right, we are 30 minutes in the class. Now we're going to start the actual content, which is fine. Gives you some reflection for the last class. Okay, water treatments, why we need it? As you know, we need to be safe and we drink water 2 liters per day. So everything we drink is going into our body. So it's very important that we drink safe, clean water. But unfortunately, in nature, most of the waters are polluted because of either natural reasons or also because sometimes mostly man-made reasons. So we have to treat it. So I'm going to show you a video about Flint water crisis that you have probably heard about a few years ago. But this will also teach us why it is critical for us to understand this. So I'm going to stop um, sharing the screen, but I'm going to share the screen from my, let's see. Okay. So.
This change in the water was particularly noticeable at that time. My youngest would tell me, Mom, it's yellow and it's a filmy, gross, foamy thing, and it would smell like open sewer. But we were being told we're still getting used to the new system. It's safe, it's okay. But it wasn't okay. Far from it. Flint's tap water was laced with dangerous levels of lead. The state knew about it and did nothing. The trouble began 2 years ago when the state decided to switch Flint from Detroit's drinking water to a new system. But the new system wouldn't be ready for 2 years. In the meantime, to save money, they switched to the Flint River water. 3, 2, 1. That first decision turned out to be a mistake, as did nearly every step the state took after it. Michigan's Department of Environmental Quality shoulders much of the blame, what a preliminary task force report calls an abysmal public response. At the time, the state agency told Flint it didn't have to add an anti-corrosive agent to the water, saying it was not necessary until 2 6-month monitoring periods had been conducted. In other words, they were willing to wait a year to see whether the water was safe. All the while, highly corrosive river water flowed through the city's lead pipes, leaching lead and other dangerous metals into the water supply, and what came out of the tap in many homes was toxic. Almost immediately, residents started complaining. Their water was brown. Some people developed rashes, became sick.
Early tests revealed fecal coliform bacteria, so the city and state officials added chlorine to the water supply and told people to boil their water. Both mistakes, which can actually increase the level of lead. At city meetings, residents were repeatedly told the water was safe.
We found the worst lead and water contamination that I have seen in 25 years. And believe me, I've seen a lot.
Residents didn't find out about the lead until this man stepped in. Mark Edwards is a Virginia Tech researcher who tested the water early last year.
It was very scary to see the levels of lead that were hazardous waste, levels of lead coming out of her tap water.
That's right. The lead levels in one home were so high, water from the tap could be considered hazardous waste. His testing led to this EPA memo, an interim report which was leaked last summer. It said the high levels of lead in the water were especially alarming because the state's water testing was flawed, so the true lead levels were probably much higher.
We were just waiting for the appropriate authorities to help Flint residents to enforce federal law.
When Flint's former mayor asked the EPA for more information, he was shot down, as you can see in this email exchange obtained by CNN. The EPA regional director writes, "The preliminary draft report should not have been released outside the agency, and that only when the report is revised and fully vetted will it be shared with the city." But that wouldn't happen until months later. Meanwhile, families were still drinking water poisoned with lead. The EPA blames the state, saying in a statement to CNN, what happened in Flint should not have happened, and that the EPA's ability to oversee was impacted by failures and resistance at the state and local levels. The state was continuing with its own mistakes, according to Mark Edwards, butchering a round of water testing. They not only tested the wrong homes, but altered the reports, eliminating tests from 2 homes that would have shown toxic levels of lead. The state says the changes were legitimate.
They fabricated a report that made it appear like Flint was passing the lead and copper rule with flying colors.
In the fall, the government admitted that there was lead in the water and Flint was switched back to Detroit's water supply. But it wasn't until earlier this month that the state of Michigan started bringing in bottled water and declared a state of emergency.
All right, so I want you guys to think about it for a few seconds and tell me what are the things that you heard that could have affected the lead concentrations or that lead to increase in concentrations. So let me share the screen again. And while you are thinking, all right, so any volunteers?
Talk about boiling the water.
Yes, so one is this says, okay, boiling the water. So that it says that boiling water will make it worse. So we'll discuss why. Any other?
Did they suggest to add some kind of anti-corrosive chemical?
Okay, I'll write it here, anti-corrosive. We'll get to that.
They talked about adding chlorine.
Yeah, I was gonna.
Add chlorine, thanks. Anything else that need? No, these are all about once they switch the water, but one thing they said is the switching of water itself led to increase in chlorine lead concentration. So we know that it's because of switch of water, switching water from the lake to the river water, switching source water. And that source water was, they say, this was corrosive. Okay. So that was one other reasons. And also, you know that there are a couple of things. I'm just going to write second side. They remove certain samples. They say this is too high, so they remove the outlier, or that's what they claim to be. They say it's justified because they are outlier. How do you know what is outlier versus what is the actual thing number? So they removed high contaminated contaminated samples to bring the average below the APL limit. Okay, so these are, so one thing they said, they did not add corrosive. Okay, did not add corrosive before releasing. It's not about adding corrosive. They say it is required to add corrosive, but they anti-corrosive, but they didn't add those. So I'm going to write it here. They did not add anti-corrosive before redistributing. Okay. So these are the multiple mistakes, and we'll learn in this class what exactly it does. Okay, so hold your thought all those, and the last at the end of this class we'll discuss that why its steps were mistakes, and I hope you'll get that answers. So all four are mistakes. Okay. All right, so drinking water standard. So what you learn here is that lead is a pollutant, and there are certain concentration you have to have. And it says that now the professor says, the Mark Edward, he's a civil environmental engineering professor at Virginia Tech. He found that when he analyzed, some of the concentrations are above the even hazardous level. So what that means is there is a standard, and the actual lead concentration standard is near zero because it's a carcinogenic. So no amount is safe. So you got to have just a guidance that how much lead you should have in water maximum. So that brings down to how do we know what is safe drinking, what is the safe level? So because of that, EPA has established this laws, Safe Drinking Water Act. What it does two things. Number one, it creates standards that everybody has to adhere to. So they do the testing based on toxicity. They determine what concentration is not safe enough. So they recommend that concentrations. So those are enforceable. Some concentrations are not enforceable, but some are enforceable. So we'll get to that. But most importantly, it creates an action plan. It forces the operators of public water system to monitor the quality of water. Otherwise, they will not do it. So they have to. So it's your rights to ask for your drinking water suppliers to give you the report if you want to know, and they have to provide it, and they do monitor every weeks. And they also the reason they monitor is because they also wanted to treat it if there is a exceed in concentration at certain time. So they have to also report it. So these are the two things. First one is the guidelines, and second one more about the action plan. And again, as I said, there are two types of standards. One is primary standard, which is enforceable, and that's based on the health related criteria, because you know that certain type of pollutants are causing health effects. So those are primary standards. But the secondary standards are unenforceable. So they are not forceable. The reason is they are based on aesthetic. So it doesn't have a serious health effect like taste. If you don't like the taste of water, they should do something about it, but it doesn't really cause that much harm. So that's why it is not enforceable. Taste, odors, color of drinking water. So basically based on aesthetic characteristics. Sometimes also it's also related to corrosive or hardness. You learn about that in this. Corrosivity is about this particular class, and the hardness you learn in the next class. But these are related to it interfere the way water is effective for different functions. Like for instance, if your water is hard, it's not going to easy to clean clean your laundry. The soap will not be effective. If it is hard water, it can also some kind of cause skin rash. If it is hard water, you can see the scale build up inside your pipe. Corrosiveness is opposite. If water is not hard, it can also increase corrosion. So we'll get to that point. But point is there are two different standards. So we have to think of both. Um, so how do you know what's the concentration? So what EPA does is determine maximum contaminant level. Means your concentration should be maximum this amount for it to be distributed. Anything beyond is not recommended, or that's going to have adverse health impact. That's based on the exposure level that you determine the risk class. In the risk class, you calculate how much exposure for if you smoke cigarette. So this is on basis of that. So sometimes the contaminants are harder to detect. So that's why instead of having the drinking water treatment systems to actually monitor them, what they do is they enforce certain kind of treatment, which is known to remove most of those particular pollutants. In this case, I give example cryptosporidium. That's a oocyst. That's a type of microorganism higher than bacteria level. They have nucleus, all that stuff. So they are very protected. They don't get destroyed very easily, but it causes a very high sickness. And so that's why to protect your drinking water wells or drinking water systems, they are designed to have some kind of disinfection. So that's the reason you need to have disinfection to remove that cryptosporidium. And so this table one, gives you lots of different types of pollutants. As you can see, there are inorganic pollutants here, which is heavy metals, and all the other ions, anions, cations, nutrients, all that factors. And then also you have lots of organic. These are organics. And if you think of organic, where they're coming from, they are coming from pesticide, herbicides. They're coming from also volatile organics like degreasing agents, paint thinners, dyes. Everywhere there are solvents to make it evaporate faster. You have those pollutants. Also, sometimes pollutants are created in the drinking water system, even though they are not in the source water, because of the whole disinfection process. We'll get to that. And the idea here is that you have some organic pollutants which are benign. For instance, think of tea. You drink tea, that's benign, that's healthy. But if you take the tea leaves and tea waters and add disinfectant in it, that disinfectant will interact with the tea leaves or the levels and will create hydroxyl radicals. It will create different types of organic, which are even worse than the itself what is there. So that's the carcinogenic. So we'll discuss about those. And then sometimes your water can contain radioactive materials like radon. Those are formed naturally in soil. So if you collect from groundwaters, the groundwater soil sometimes has radon. So you have to remove those radons from those before its distributions. And then most importantly, microbial pollutants. They cause acute toxicity like cryptosporidium. If you have pathogens in drinking water, that would cause instant sickness or within a day, as opposed to organic or inorganic pollutant, which is a chronic illness. So that's why a lot of times we got to measure it. As you see, these are different pathogens, but a lot of times pathogens are very difficult to measure. So that's why what they do is they look for indicator organism. Means what is that means? The assumption here is that if you have indicator organism, that means the pathogen might be present. So it's not a direct one. So that's why you see over here, coliforms, enteric viruses, they're all related to indicator organisms. Okay, so this is same thing as heterotrophic plate count. So what I want you guys to understand is that these are the different lists. There are like over hundreds of pollutants. They have maximum contamination level. So what the message I want you to get out here is that there are only hundreds of chemicals we do it. That doesn't mean that there are enough. That's the only pollutant present. In fact, there are thousands and thousands of pollutants. So just because you don't have those hundreds doesn't mean that you may not have pollutant. That's why there are pollutants like PFAS, which has a lot of utility company not measuring it because they are not enforced yet. The moment it has MCL, they have to monitor it. So the PFAS is a perfect example. Even though we know this is bad, we're not monitoring because EPA has not come up with that number yet. So it takes time. And then there are other contaminants like unforeseeable, maximum contamination level goal. So here it is not foreseeable. It just give a guidance or recommendations that you should design your treatment such a way that the concentration that will achieve with that levels. So again, these are the number you can see: corrosiveness, fluoride, irons, manganese, odor, PA, silver, all those things you can see over here. Okay. All right, so now that you learned this one, let's see how much you have paid attention to um, the small quiz about which one of this standard is enforced, MCL or MCLG, maximum contamination levels or maximum contamination level goal. Few more seconds. We have still around 20 students who could vote. Okay, I'll close it in 5 seconds. All right, so I'm going to share the results. So majority of you, 92% says this one and 8% says this. Okay, again, right answer is A. You can see MCL is not enforceable. Okay, that's not related to a health effect. This is more about other aspect. Okay, so now that you learned the driver of the why we treat water, let's get to how we treat it. Okay, so if you think of drinking water, you have to think of two different facts. Number one, what's the source? Because source determine what kind of treatment you will have. Usually, most of the drinking waters that we use has either surface water source, something like lake in this print, that video, and that has a river. The lake was the original source, then they start collecting from river. Then many places also groundwaters. So based on what's the source, you know that certain pollutants will be present more than other. For instance, if you have surface water, you will have lots of turbidity, means you have lots of particulates. But if you are pumping from groundwater, you don't have lot of particulates because they are filtered out in soil. So that means your the types of treatments you'll have will be different. On the other hand, if you take from groundwater, it will be very salty because it comes from soil. So soil releases ions. So that could be, it has high, it could be hard water. It could be, hard means hardness. It could have lots of ions, salt, and that you have to remove. So that's why you have to know what's the source of water. And once you know the source of water, you can change the treatment system based on different types of processes. So you have physical processes like, anything that you can feel the size. So that's why it says sedimentations is a physical process. Filtration is a physical process because it's basically a strainer. You take a strainer, pore size are there, you add water, so all the particulates will filter out. And the chemicals treatment system as coagulations. Coagulations or flocculations. Flocculation is kind of sedimentations, but coagulation is chemical processes. And then biological process, basically disinfections. Okay. So you have to look for all those processes. So let's say it's a series of processes. It's not like you have to use one process. You have to do in multiple series. And there is an order to it. There is a reason why certain things are done first before than other. For instance, this is a
What
typical.
were the biological?
Yes.
On the previous slide, what was the biological? The disintection. Oh, disintection. Okay.
Um,
Disint.
uh, Question here.
Yeah. Yeah. Like what was the okay disintection?
Disinfections. That's
Oh.
the end here.
Oh. Okay. Okay. Okay.
Okay.
Cool. Thank you.
This is filtration. This is sedimentation. This is flocculations. Then there are storage. Sometimes it has to be stored before it supply because to maintain that 24/7 treatment.
Thank you.
Everything actually can affect the contaminant concentrations. Okay. So this is the sequence for a surface water. As you see, this is a sequence for surface water treatment plan. That means the source is surface water. Okay. So it says surface source. So first thing you have to do is what you are removing at different stages. The first one is a screen or grid chamber. The reason I say Surface water can have leaves, debris, because exposed to atmosphere, things will dump there because of storm water. So you got to have a screen. So that's remove large particles, okay, or debris, okay. And then second one is primary sedimentation, so which is basically a big clarifier. So there are a couple of questions here. I didn't see that. How boiling water increases the fluoride? It's not fluoride. We'll talk about why boiling concentrates, while boiling would increase the concentration of lead. Okay, we'll get to that. Um, and then the second question was, why is disinfection biological? Uh, well, it's you add chlorine, you add chemicals, but the effectiveness of disinfection depends on biological organism. Uh, some some bacteria would die very easily with chlorine, some are not. So that's why I also write a little bit of it's a combination of biological as well as chemical process. Okay. The effect is biological, the cause is chemical. Um, okay, so primary sedimentations, that's basically removing particles or sediments that is heavy enough to settle, uh, that can settle, okay, by gravity. Once you remove those, you have very fine particulates, very fine particulates. Those cannot, this just takes long time to remove, something like around 1 micrometers to 10 micrometers. So these are the particulates that takes many days to remove those, maybe like 24 hours. It's not practical to hold that water for that long. So that's why you got to initiate that process much faster. That's why you add coagulant. What coagulant does, it makes them stick with each other and become larger particles so that it can settle. So that's what it does. Coagulant is basically adding a chemical so that it can makes the particles sticky and then create flock. Flock means small particles collide together to become large flock or larger particles. Okay, so think of this. This goes to, and then it can settle by gravity. Okay, um, so this is called flocculations, and this is flock. And then once you create the flock, you have to remove them by gravitational force. That's why you have to create another sedimentation, secondary sedimentations to remove them. Once you finish all that, you want to remove some of the very fine particulates by filtrations. So that's why you add filtrations. It can also remove some bacteria. So that's why you want to remove some microorganism by filtrations. So this one remove fine particles that still there created in the during the process, and some pathogens, and also organic, dissolved organic. Okay, because dissolved pollutants will not be removed by any process that I just described before this. So you want to remove some dissolved organic or dissolved pollutants, so that's why you have filtrations. Once you remove those, at the end you add disinfectant, and that's the disinfection. So this is a really removing pathogens. Okay, and then you add fluoride because that fluoride is important for the quality. So this whole process is removed by fluoride. Sometimes you might have to add fluoride because surface water concentration doesn't have enough fluoride, which is healthy for us. Okay, that's why sometimes you have to add, then you distribute. But if you do the exact same process for groundwater, this is a little different. So I put on the top what we just described. So if you look at the groundwater, what is missing here? The screening of grid chamber is missing because, as I said, groundwater you don't expect large debris, so that's why you will not have that requisition. But sometimes groundwater contain lots of volatile gas, so that's why you have to have aerations to remove gas. Okay, bubble out all the gases. For instance, ammonia, methane, all that kind of gas you want to remove. And then you have to add, you have to increase flocculations. Because you'll realize that for flocculation or coagulation to be effective, it has to have high pH. So for pH adjustment, so you want to increase the pH, that's why you have to add limes or sodas. You'll learn about that process next class. But point is, you want to change the pH or add some ions, it will increase the efficiency of flocculations. And once you have flocculation, you will add that sedimentation, remove the fine particulates. And in the process, because you are increasing the pH or the flocculations, that remove carbon dioxide. So the pH will become high. So to put it back, lower the pH, you add carbon dioxide. So you are adding CO2 to make the pH decrease, because here pH increases, you have to balance the pH before you do filtrations, because otherwise filtration will not be that effective. And then you do the normal processing like before. So as you see, all the different reason, the series is based on what's the characteristic of water. So these are all logical decisions. Any question?
Is fluoride not added if it's groundwater, Professor?
Yes, because fluoride, normally when rock dissolve, fluoride comes from the rock.
Oh, okay.
So usually fluorides are not present in the surface water, but groundwater you have enough of them.
Thank you.
Okay. Again, that's optional. It's not necessary that you have to add, but sometimes you do monitor the concentrations. Okay, so here's the questions I want you guys to think about. You see that both places I put disinfection at the end. The reason disinfection is needed is because to remove pathogens. And so why we don't do disinfection at the beginning? Any suggestion why?
Would some of the chemicals react with other things that haven't been removed in the water yet?
Yeah, Ramiro, that's a good suggestions. And Judge actually sent by chat window, and that was also correct answer. It says that we don't want to use disinfectant to remove other pollutants, because if you add disinfectant before, you have so much stuff in water that you don't need to, that disinfectant will be absorbed by that. For instance, you have turbid water or particulate water, then you add disinfectant, those disinfectant will absorb on the particulates, and then there will not be effective enough disinfectant remaining for the pathogens. In fact, remember these answers. You'll use that to understand why Flint water cause other disease. Okay, so we add this one so that the disinfectants are not wasted by other by adsorption or reaction with unintended target, like particles, all that stuff, because you want the disinfectant to be available just to remove pathogens, nothing else. So once you remove all that, then you will apply disinfectant to save cost. Okay. And also in this case, if you see filtrations, filtrations require here you remove organics, and a lot of times those organics are removed by, this is basically sand filtrations, right? And what it does, you have sand particulates, okay, and the organics, the microorganism is not just it's just not the pathogen. There are natural microorganisms which are okay, so they grow on top of that, so they create this biofilm. So I'm going to create these things, so they create this biofilm, okay, and that biofilm can actually remove organic pollutants. So organic adjure on this one. So you need that biofilm for filtration to be effective. So if you add disinfectant before, you'll kill them, and so that you're not going to have efficient system. Not only you'll spend a lot of money, but also you'll decrease the efficiency of filtrations. Okay, so these are a couple of reasons you can think of. Okay, so let's go to the individual process. Those are, again, you know already this concept, mass balance. So you wanted to just apply very quickly. This is a, so here sedimentation. So the first thing you have to think of is how fast a particle can settle. So if you think of a particle, this is a small particles. So let's say that's the particles. Okay, and it's going to settle. So it has three forces that apply on it. The very first one is very easy to conceptualize is this weight that pull them down. But there are two forces that makes the particles stay suspended. Number one is a drag force. It's the same thing as friction force. So think of, if you're driving, you put your face or hand outside, you'll feel that friction because of fluid mobility. So the faster the velocity, the drag force is be faster. So that's why drag force is depends on um, the velocity of the particle speed or settling velocity. And if you have larger diameters, it will have also higher drag force. And also it depends on the viscosity. Um, so basically, if you have viscous liquid, the friction is higher, and the fluid has a lot more frictions. So that's the drag force. And then there is also buoyancy, because that is the moment you put the particulates, it displays that some amount of water. That is the amount of the buoyancy. So that's the basically weight of the water is displaced. So that's why volume of particles times the specific gravity or density of water times acceleration due to gravity. If you think of the weight of the substance is basically the same thing, same formula, but the only difference is the weight of the particulate. So this is the two things. This is density of particles. This is density of water. Okay. And if you think of what is the volume of if you think of volume of this is volume of particles, that's basically 4 by 3 pi r particle q. Or if you make it density, the diameter, so it's a 4 by 3 pi particles q. So that will be um, pi by 6 dp q. That's the volume of particles. Okay. So if you wanted to know the velocity, you have to think of when it attained the terminal velocity. Means at that when terminal velocity means the net force on the particles is zero. That means there is no acceleration due to gravity. So that means net force is zero. That's basically d by dt m, or not d by dt. Net force is zero. I'm sorry, this is I messed it up. So net force is zero. Okay, so that means m dv by dt is zero. Change in velocity or acceleration is zero. That means velocity is constant. So settling velocity is constant. That's called terminal velocity. Okay, terminal velocity. So net velocity is zero. That means the net force is zero. So
I
what?
have a question before you move on. Did you intentionally say that VS is the same as VP, or was the arrow just there and that was already there?
Say again.
And the FD equals 3 pi viscosity times VS dP. There's
Yeah.
an arrow above VS that was put before VP was written. So I'm just
Oh no,
wondering
this is
if.
velocity is velocity of particles.
Okay, thank you.
This one is for. Okay. All right. So let's see now. The net force is zero. That means what I'm saying is Fg should be equal to net downward force is same as net upward force. Okay. So if you put this value here, let's write it. Fg is if you see Fg, this is Vp. So another way to say is Fd is Fg minus Fb. The reason I do this one is because easy to solve it. So Ft is 3 pi, there's a viscosity time velocity of particles and d particles is equal to fg. If you see the size, this is volume of particles times density of particles times g. So volume of particles is common and g is common. So you take that as density of particles minus density of water. So if you know what is the VP is, VP volume of particles, we just solve it, pi by 6 dpq. You substitute that here and you solve for Vs, you should be able to get this one. Okay, so that's the final answers. So what does that mean? The velocity of particulates depends on the change in density or the difference in density. So that's basically difference in density of particles to water. Okay, and size of the particles times square divided by the viscosity. So what that means is velocity. So your goal is to settle as quickly as possible. So you can settle that way. If your dp is increases, the larger the particles is obviously it's going to settle faster, and the delta b is higher. What does that mean? It's heavier than water. So that means if it is lighter than water, obviously it can settle. And then also viscosity decreases, because if it's more viscous, then the friction will keep it floating. Okay, so that's basically the reason how we can increase the velocity. So now that you learned the theory, let's apply that in the actual design. Okay, so this is how it works. You have water moving in, and most of the time you want the particulate to settle. So imagine there is a particle here. Because water is moving left to right, so there is a time, there is a velocity by which it will moving on the right, towards the right. But as it move right, it also gravity or the net force is going to move, make it move down. So the trajectory will be like an angle. So after a distance, the distance that it can come down is hp. So your goal is to remove all the particulates, and you can remove all the particulates when the hp becomes the actual depth of the water. That means if it touch, let's say I do it another, if it touch the surface, that means it is all removed. You can assume that way. So that's why, you know, a lot of times we write the equation on hp. Okay, so hp is basically um, is the velocity of, because think of, you know, it takes time from here to here is the same time it takes from here to here. Okay, so the velocity, it move as it move this way, so the distance if goes that side, it will be also similar. So what it does, it basically hp is the velocity at which it settles times the amount of time it stays in the system. So this is called theta, is retention time. So that means the amount of time a particulate stays in the system. Okay, so if you multiply times the velocity at which it moved down, you should be able to cover that distance. So basically the distance is equal to velocity times the time. Okay, so if you think of what is the time, is you can determine based on the flow rate, because if you increase the flow rate, it will stay less time. So the time here, time is volume of entire tank. Okay, so the volume of um, the clarifier, so that's VV divided by the flow rate. So this is flow rate, this is volume of the tank. Okay, the clarifier, volume of tank. So if you multiply, that's the time, that's the height, okay, effective height that you have to cover. So what it means that if you can, that hp becomes the entire depth of the system, then you remove all the particulates. So that's the assumption. So normally what you do is you can measure the height. So what you measure is overflow rate. Overflow rate means basically how much times it takes, or what's the velocity at which things are moving out of the system, assuming that you have removed particulates. So the question here is that if overflow rate, think of this way, how the rate at which you are removing the particle out of the system, That's the overflow rate. And the settling velocity is the rate at which it's settling. So if they are equal, that means what you are saying is whatever time available for this thing to overflow out of the system, that's enough time for things to settle. So that means if the overflow rate, velocity of this is the overflow rate, okay? Overflow rate is same as particle settling, that means all particles will be removed. What it says that it has sufficient amount of time before it to settle. If overflow rate is let's say greater than Bs, that means you are overflowing much faster than the settling velocity. The fraction it is bigger than that will the percentage will remove. So that means the percentage removed would be 1 minus velocity of particle by velocity of overflow. Okay. If overflow rate equal to velocity settling, that means 100% removed. So that's 0. Oh, I'm sorry, this is not 1 times 100. Okay, so that's the idea for designing. So overflow rate again is about h divided by theta, or the retention time. Basically, we are saying how long it takes for particles to move from the entire height. So if you multiply a flow rate, both side, basically the theta equal to this value, if you substitute here, then you'll get the final answer, which is Q divided by AB. So what is this area? This area is not the side of the wall. This area is the entire area. This is AB. So think of a overflow rate means how long it takes for the water height to rise up to the surface. So if you are pouring all the water in your bathtub, it's basically how fast it's moving up. Okay, so that's the surface area is accounted for overflow, not the wall. So now that you know these definitions and all the stuff, let's solve the questions. Again, critical settling velocity has to be equal to overflow rate for things to be removed. So if you solve this one, overflow rate is equal to Q by AB is velocity of settling. So velocity of settling, you know from the previous equation, that's acceleration due to gravity, particles density difference times particles size square divided by 18 mu. If you know this one, you can solve it for AB. Okay, that's the design, how big the clarifier you should have, how big the area should be there. Q is the amount of volume of water you need to treat. So that's basically this. This is the design of clarifier or the settling tank. So if you see in the original pictures here, this is that D. Okay. Basically how big the size it should be. So that's the only design factor you have to do. And it doesn't, one thing interesting you have to know, the removal is not dependent on the depth. Okay, it's only depend the area. If you see this equation over here, because the reason is the way this is designed is you are overflowing here. Okay, you are not collecting water here. So anything, even the particles move a little bit bottom of that value is already removed because that's blocked the system. It's only removing from the surface. That's why depth is not really affecting the rate, but depth does affect the hydraulic retention time. Okay, that's that this one will affect the depth because it affects the volume. Any question? So let's solve the example. That way you'll know how to solve this one. A drinking
Can I
water.
ask a quick question? I'm sorry.
Yeah.
I just wanted to clarify. AB, does it change with question or it's constant? This is like always, AB is always this equation, right?
AB is the area, the size of the area that are required to remove all the particulates. So AB is the size or the area of clarifier to remove all particles with size dp or bigger. Okay. So all that means is this: if you know the particle size, you will be able to calculate the area needed.
Thank you.
All right, so let's solve example. A drinking water treatment plants use a circular sedimentation basin. It says circular size, so that means it says the area would be pi and d square. Okay, to treat 303 million gallon per day. Okay, so that's the flow rate. So the Q is 3 mgd. Okay, so you have to change to the meter cube. So that's another thing you have to do. So how much meter cube per day? That's something you have to do because the size are given different way. And it says use a circular clarifier. Okay, so that area is circle. That means this area is pi this by 4. Okay, that's the d. User flow rate, so it says 1 mgd is 0.438, so that means you can calculate 0. You multiply that value. After storm occur upstream, the river often carries 0.01 millimeter sealed particles. So that means says the particle size is given 0.01 millimeters. So if you do that in meters, so 1 millimeter is 100. So that will be 0.01 times 2 meter. Average density of particles, so that's basically particle density is 2.2 gram per centimeter cube. The silt must be removed before the water can be used. That means it says 100% of the particles has to be removed. The plant clarifier is 3.5 meter deep. So this is 3.5 meter deep. Okay. And it says the diameter is 21 meters. So this is 21 meter. So if you know this one, diameters and depth, you know the volume. Okay, so what it says is you know the AD, you also know the volume of the tank. Okay, so pi d square by 4 times depth. Okay, that entire volume. If you know the volume, you also know the theta. Theta is volume divided by flow rate, or the time, hydraulic retention time. So that's given. So again, I'm just going to write it here. So depth times pi d square by 4 divided by q. Everything is given, so that means you can calculate the time, the hydraulic retention time. It says the water is 15 degrees Celsius, so that temperature is given because that means you can calculate, because water has a specific viscosity at 15 degrees Celsius, and water density is also going to change at temperature. So that means you should be able to know what is that value at 15 degrees Celsius. Usually in the questions that are given to you. There is a table in the book, you'll be able to find that when you solve the actual homework question. But in this example, I'll give it that to you. In exam also, I'll give it that to you. So what is the hydraulic retention time? Well, I already solved this one. Okay, you can solve this one by just having this number here. Everything else is given. Depth is 3.5 meters, so that's the depth. And D is given, Q is given. Just convert them to right units, all meter square. So this should be meter cube. This is meter cube per day. You should be able to get that value in day. Okay. Will the clarifier remove all sealed particles from the river water? So that's the question. Is this going to remove everything? So how do you know it's remove everything? You are basically comparing the velocity of particles versus overflow rate. Okay, if the overflow rate is is uh, is less than or equal to velocity of settling, it will remove everything. So you are just comparing that value. So all I'm asking is the calculating Vs and compare that to Vo or V0. V0 value is Q over AB. So if you see V0 equal to Q over AB, which is our base. So as you see, this is all given, so you can calculate this value. What you don't know how to calculate is velocity of settling, but that number is given to you. So I'm just going to write that here. So again, G is 9.8 meter per second square. Density is, I gave you this number here. Particle density is, what is the number? Somewhere it's given 2.2 gram per centimeter cube. So that will be, actually, if you calculate that value, this will be 220 kg per meter cube. If you convert that, okay, I just jump it ahead, 2.2 gram per centimeter cube. You could change that to 1000 gram is 1 kg, and let's say centimeter cube. So 100 centimeter is 1 meter. So Q is equal to the same thing. So when you do this one, it's all come to 2200 kg per meter cube. Okay. Minus the water density is 999.1 kg per meter cube, times particle size. Particle size is given to you. This is here. That will be 0.01 10 to the minus 2. So that will be 10 to the minus 4. Okay, minus 4 meter square divided by 18. Mu is the viscosity. So that will be 0.00114 kilogram by meter second. Okay, so if you see,
Professor, I had a question about something.
huh?
Sorry, I had a question about something. So for the diameter, would it be 10 to the negative 3 instead of 10 to the negative 2 to convert from meters to millimeters?
Oh, I see. You're right. I made a mistake. 1 millimeter is minus 3. Thanks. So that'll be minus 5. Thank you. I made mistakes. Okay, so you have everything. If you see, you are calculating velocity, the kilogram cancel, and you have meter square here, meter cube, so it will be 1 over meter, so this will be cancelled, and this is 1 second cancel here, so this will be meter per, whatever the number is, meter per second. And if you want to if you want to say the VO, if you see VO value, this one you can also calculate meter per second instead of meter per day. So whichever way, just change the unit and then calculate. The percentage removed, again, velocity of times 100. Okay, if it is VS, if velocity of what you calculate equal to VO or less than, let's see, not less than, if greater than equal to the, then all removed. That means you are settling much faster than the before it overflow. Okay, but if it's not, then percentage remove, you can calculate this value. Any question? Okay. Next question. Next is coagulations. Again, everything that you can remove as a heavier particles, larger size you can remove. Coagulations, those are very, very fine particles. If you calculate the value time it takes, it will take probably multiple days or more than 24 hours. You can't hold that much water for that long when your flow rate is much higher. So that's why for that you have to artificially increase the settling by making the fine particles larger particles, by making them stick with each other. So the way it works is if you think of any particulates, okay, it has, whether it's a clay or silt, it has net negative surface charge. If it has net surface charge, it is going to, hold on a second. Yeah, no, I'm still in class. I'm sorry. So if it has negative charge, so what does that mean? If you have another particulates, Okay, if you bring another particles close to here together, it has negative surface charge, then it is going to repel with each other. It repel with each other. And because of that, it stays suspended. So your goal is to make them stick with each other. So how do you make them stick with each other? You have to reverse that negative charge. You have to at least make them neutral charge. So the idea of coagulation is um, decrease or neutralize surface charge so that they don't repel against each other. Okay. So how do you do that? You have to add something positive. So that's why the coagulants are basically the ions are positively charged. So what you do is add either iron 2, iron 3, or aluminum 3. Okay. Obviously, you can add just as a positive charge. You also add equal amount of negative charge. So that's why sometimes you add iron chlorides or iron sulfate. If we Cl3, if it is 3 charge, this will be this, or aluminum OH. Okay. So now you might say, now why you are also adding also negatively charged, but why they are not interfering? The idea here is that the attractions. Okay, the chlorines are such a big molecules, it's not going to be close to that surface. It will be it will not be interfering the absorption process. So iron it will make it let me see, there is some voice coming to mute. How to let me change to mute. Okay, I asked to mute. Okay, that's good. All right, so that's that means you are going to change the surface charge. Okay, that's why you are adding those things. Okay, so this is the process. So that means you are one of the reason that's why aluminum is added. Alum, that's called aluminum sulfate. The idea here is that you add alum, that aluminum will precipitate with hydroxide in water, and that creates these very fine tiny particles. And those tiny particles will stick with another particle. So you're creating artificial lot of very tiny particles, and they stick with each other. And anything that's also in water regularly, that will also stick with each other. Then you create this big flock. Okay. Um, so as you see, this process require you have um, carbonate, and usually groundwater has lots of carbonate. So that's naturally also carbon dioxide is dissolved in water, so you'll have naturally high concentration of SCO3. But if you don't, you have to add something like a calcium hydroxide, because your goal is to increase the pH. Okay, so you add OH to precipitate this one. Okay. So that's just basically mechanism of coagulations, and that's all. So the principle here again is you reverse the surface charge and precipitate these fine particles by increasing the pH charge. So I'm going to show that two step. Number one, reverse surface charge from negative to neutral, and then increase pH so that you can precipitate aluminum salt. Okay, that weighs all these things. This is precipitate, that's become solid, it will precipitate. And those fine precipitate is going to interact with other particles and settle it out. And so once you create that one, you have to mix them together so that it can create the large plug. So all you are doing here is just mixing. So this design is nothing, it's just you are mixing the entire thing. So mixing is again needed for these fine particles to come close to each other. Okay. because you are only going to create flock if they come closer together as much as possible. So what will happen is you have these particles moving here and this particle moving here, and they collide. See, this collision can make them stick. So now if you have like 10 particles collide with each other, how much percentage of them actually stick? So that's called collision efficiency. This is no, this is the amount of particles stick together. So that's collision efficiency is how many particles collide, what's the probability of them colliding. And once they collide, doesn't mean that they're going to create flock. So that's called attachment efficiency, alpha. Attachment efficiency, alpha. So alpha is 1 means everything that collide, 100% of them stick. Okay. Going to stick. Okay, so that's alpha could be equal to 0 to 1. 1 means 100% efficiency. And collision efficiency is all about how was the probability of the colliding. And collision efficiency depends on size as well as the mixing rate. If you are mixing too much, you are more likely going to collide them. So those are the few things. So collision efficiency depends on the power of the mixing. Okay. So based on that, this is the mixing intensity. So how fast you want to mixing, and the intensity depends on the power. So this is power of that rotation. When you rotate something, it's just like energy that you consume. So then it becomes power. Okay, power of the mixer. Okay, so that's here. Yes.
Could you go over, sorry, adding calcium hydroxide in coagulation, please?
Yeah.
Thank you.
So the reason we add calcium hydroxide is to increase pH. If you don't increase pH, they will not precipitate. Because if you see, the precipitation is occurring because of OH ions, right? And that OH ion is naturally present if your pH is high. If not, then you have to add pH, COH. So this OH is going here. Okay. And you'll learn that more when we discuss about hardness in the next class. But here, just know that all you are doing is increasing the pH.
Okay, thank you.
Okay, so mixing rate, that's basically operational definitions that paddle how fast it's going to move, because that's the energy, that's the amount. You don't want to mix too much because that's a cost to you, extra cost. So that's mixing rate depends on the power and the viscosity, inversely proportional viscosity, and the volume of water that you need to treat in that tank. Okay, so as you see, think of conceptually. You need more power if you have to treat lots of water. So the mixing rate is depends on if you have lots of high power, then you don't have to, intensity will not be the so G increases if power increases. That makes sense. If you have more power, then it's going to move faster, mixing rate. And then volume, the volume of water that you have to treat, if decreases, mixing rate would increases, because if you have larger volume, that means if more volume, the mixing rate will be less, because you need it takes a long time to mix. And second is same thing as viscosity. If your viscosity decreases, your mixing rate will increase because there are less frictions. So as you see, anytime asked question, you can think of conceptually to answer it, or you have equation to explain that. You need equation if you have to know how to calculate. For quiz questions, most of the time is concept, so you should be able to understand that. So flocculation rate, again, mass balance equation. This is something you are asked to calculate sometimes. This is just, we learned that before, so I'm just going to quickly write it. Changes amount of particulates that become flock or removed because of flocculations. That's dN over dt. That's number of particles that can create flock. Okay, that depends on the rate at which the flock can occur times the number of particles present. And that K, or the rate constant, it depends on alpha. So alpha is your collision efficiency because you want them to collide. So I actually wrote reverse here. So let's write this one. Let's call this is attachment efficiency also is a factor. So I just didn't, we don't need to write it here. This is, I just write the wrong notation there so that you might be confused here. So this is collision efficiency and flock volume. So this is basically the size of the flock, and G is the power mixing rate that you just calculate here and divided by pi. So that's the rate. Okay. And so alpha, this is usually given, that depends on particle properties. You can also estimate, but you will not learn how to calculate here. Usually it's given to you. Flock volume is again same thing. The volume, basically the number of the size of individual particles times the number of particles that create the flock. Okay, so initial amount of particles. So what I'm saying is you have, let's say 3, 4, 5 particles. 1, 2, 3, 4, 5, 6, 7 particles. They create 1, 2, 3, 4, 5, 6, 7. Okay, so that's the flock. So what you're saying is the flock volume, the entire volume would be the size volume of individual particles times the number of particles that create the volume. So it's here 7 times the pi dp of 6. So this is dp is this individual particles that create the flock. So if you know this one, you should be able to calculate that value. So let's solve a question so that you know how to do it. So to improve the settling of 0.1 millimeter particles, as example, complete, let me see. In example 1, completely destabilized by adding alums and are passed through one of the two sides of the well mixed chamber. So I'm just going to explain that what is given here. So that's the mixing chamber, and you're adding at certain flow rate Q, and the number of particles are N0. After flocculation, there is a remaining amount of particles leave the system. That's the N. Okay, so you're adding N0. N is the smaller amount of number of particles remaining. Everything else is settled. So that's B is the volume of things, and R is the rate. This is dN by dt. And this is CSTR. That means the concentration, what is inside the system, is same as equal outside the system. So if you do the mass balance, so same thing, basically you are saying Q and 0 that's coming in, it should be what's out plus what's the reactions. So dN by dt times volume. Okay, so everything reacted plus everything leaving the system, it must be what's coming in the system. And all you have to do is solve for N. And this value dN by dt, you know, this is minus Kn. Actually, dN by dt, there is a minus term here because this opposite side. So that would be, I'm just going to write it here just to make it easier, because what's leaving the system has a negative term. So that's going to be alpha for G phi n. Okay, and this value is also given here n0. Okay, so that doesn't mean n. The point is you have to n, so you can calculate n0 by n if you take the n other side, and then you have a factor here. If you take the q out, this is divided by q, so it will be 1 plus some value here. Okay, and you can calculate that, and that's what is given, asking to you what is the average diameter of living particles.
Professor,
Yes.
I have a question. Is that's the area, right, at the denominator of
Yes.
the, yeah, area times flow rate? Okay.
So there are question why it says it's negative, non-negative. So if you see what is the actual mass balance equation, so this dN by dt in the system would be coming in minus coming out minus reactions, right? So this is steady state. So this is 0. So that means in would be out plus reactions. So this term become positive here. So that's why I wrote it here. Okay. That's just shortcut for me to check the example in the book. You should be able to find that answers. It's already solved in the book. So this is written here. And solve for n. Okay, so what I'm going to do is, because we have less time to 7 minutes remaining. So what I'm going to do is explain filtrations, which is basically how much it's like a few minutes. I'll explain it at 2-3 minutes. And disinfection, you already know the rate, because these are all basically dN by dt. So this all that stuff. So I'm going to explain in the recording, which will be another 10-15 minutes maximum. What I'm going to do is I'm going to play this video, because we want to know why this disease occur during flint water. So I'm going to play this video and I'll ask those questions so that we can discuss before we end this class. So stop share. I'm going to share the screen for the video.
Follow that breaking news from the Flint water crisis and the possible link to a spike in Legionnaire's disease in that area. Our chief health editor, Dr. Parthanandi, joins us now. And Dr. Nandi, for people at home who are worried right now, they don't know what Legionnaire's disease is,
Right.
and how serious is this?
Yeah, and it can be serious. So first of all, I don't want people to panic. I mean, first of all, Legionnaire's disease is a serious form of pneumonia that can be caused by the bacteria Legionella, and you can have, pretty bad symptoms from it. The thing is that, we don't know for sure if this is related to the Flint water crisis. When we see a lot of cases, we say, let's investigate and find out more.
So Doc, when you think of Legionnaire's disease, if you know anything about it, you think of like hotel rooms, the air conditioners, things like that. How does lead in the water possibly relate to this?
It's not an absolute relationship, but the idea is this: if you've got lead tainted water, the water isn't perfect, right? So you then say, okay, is the water contaminated, and could it then lead to the spread of the Legionella and Legionnaire's disease? And so we don't know. And you're absolutely right. Most people have it in place where warm water is, so hot tubs and cooling systems. So, and indoor, the more complex the plumbing system, the bacteria can sit there and grow and spread. So, we're still trying to figure it out. But I think it's important for people to be aware, because there've been a bunch of cases in this area, and we got to find out if you have it, get treated.
Yeah, and people are worried about anything right now. So tell us about the symptoms and how do you treat
Important. So if you're going to have to watch out for things like fever, headaches, aching joints and muscles, lack of energy, loss of appetite, cough, difficulty breathing, really important, chills and chest pain. Now, if you do have these symptoms, see a doctor. It's important to get an antibiotic early, and early treatment reduces severity and improves chance of recovery. And finally, regularly maintaining clean water sources. So if you're working in those kind of places, like, if you're maintaining a hot tub or domestic water heaters and air conditioners and fountains, make sure they're clean. So I think those will help prevent it. And I think just awareness, and if you do see any of those signs, talk to your doctor and then find out what's going on.
So does it spread person to person?
It's not, that's a great question.
Okay.
It's not spread that way. People can actually, this is what's important. You can walk by and inhale the water droplets and you can get infected that way. So it's not a person to person, but it's the water supply. So in our, in most cities, you don't really see it because the fact the water supply is clean. So it's an urgent need for us to look at the water supply in Flint, make sure this is not related. And if there is, take corrective action immediately, because this could be a big problem.
All right, so I think this is they go on talk about different things about Legionnaire disease. That's not the point I want to come across. What I want to say is, did doctor answer the questions why there was a Legionnaire disease in the places where there was a lead outbreak? So let me share the screen again. So any volunteer, did the doctor answer? He says we don't know. He didn't say it. But now that you have learned all that stuff, you learn about disinfection, how disinfection works. Can you guess why there was a high chances of Legionnaire outbreak, the place where there were lots of lead?
It's probably just since, I mean, there's lead, the water just wasn't treated properly. Like there was a lot of steps that they skipped. It's like, for example, they probably didn't do the disinfection portion, and that's why there's bacteria.
Okay, so the point here is this. Legionella bacteria grows everywhere. That's what you said is a kind of similar. So think of some clue that says R chlorine. Okay, they added chlorine because they thought this is surface water, is must be pathogen, so they added more chlorine. So when they added more chlorine, it should have killed the Legionella disease, right? The any bacteria, but it didn't. The reason is when you add chlorine, it's corrosive water, so the pH dropped. Okay, pH drop means it become acidic or more corrosive. Okay, when it's more corrosive, the whole idea here why the lead come from is because of the pipe. Okay, if you see what's the lead come from, the pipe, you have this scale form, and that corrosion products has dissolved. Okay, so when they dissolve, it has also lead came out in the water. So that coatings, all the things that the pipe had is all dissolved out. And so that means if you have a lot of these turbid particles that you see the water, that has all these fine particulates. Okay, and so now those particulates, as I said, these particulates come out, and then you have chlorine. So this chlorine is not going to come to find the bacteria. It's going to be absorbed by these fine particulates. So that means this chlorine disinfection is less effective now because you have so much turbid water. So now this cold, warm water, all that stuff. So the Legionella bacteria survive there. But now because this chlorine is no longer working, so they are now going to grow much faster on these particulates. So that's how they find these nutrients, all that stuff. So they grow. So again, because you have lots of turbidity because of these corrosion products, and that makes the Legionella bacteria survive, makes the disinfection less effective. So again, it could not kill the bacteria. So that's the reason we'll discuss about that. I'll solve this a particular examples. Um, so now we learn what we learn here. Um, to learn, so the point is how to minimize lead concentrations. So again, I explained this one. I just want to write it. More turbidity implies that less chlorine available for disinfections. That means bacteria grow. Available. That's the answers. But the last one is how to minimize it. So this is the last. I think I probably put the wrong table, long video link. But what they recommend, they says that flush the water. If you want to decrease the minimize the amount of lead, flush the water before you drink it. The reason is if the entire system build up over time, because the moment you are not using it, they're all dissolving. So that means you flush water for some time so that all the residual amount of that murky water is being washed out. So flush for a while before you start collecting water for drinking. And second thing they say is do not boil. The reason is if you boil it, all the particulates has lead. If you boil, the dissolution increases. So if you boil the water, lead will dissolve. Okay, this Pb will dissolve. So do not boil it. So that means do not use the hot water. So you have two options, cold water or hot water. Always use the cold water. That way the pipe joints are not dissolving more lead. Same way. Okay. So I guess, the fact that my son is coming here, that means that we are out of time. So I'm going to stop share here. I just want to say that read this one and also watch this video, 50 to 1 hour video. This is this great example of this documentary video if you want to know more about Flint water crisis. Next class we'll learn about alkalinity, hardness removals, all that stuffs, what makes the water hard, what's that effect, and these are just couple of things that you want to I want to highlight that this is 20 minutes. Quiz will be next week, and that's open like last time, 24-hour windows. Then we have midterms. Okay. All right, I'm going to record the rest of the amount, which is another 10-15 minutes video that I could not cover. I'll share later, but that's the end of this class as far as what we wanted to cover.
All right, Professor. So the quiz, you said that it's next week, right?
Yes,
Or
next
this
week
week?
on after Wednesday. So Wednesday is holiday, so I'll release on Thursday, like last time, like you guys did. Okay. So you
Thank
have
you.
24 hours, like last same thing. It will be released on Wednesday night. You have or Thursday morning. You'll have until the Friday morning, whichever way works for you.
Professor, just to want to double check, when is your office hours for this week? The same?
You know what? I should have office hour because usually office hour is after the class. So
Oh, okay.
let's set a time. So because I'm spending now entire class, so there is no office hour by default now. So I want to make sure there is office hour. So which time? What I'll do is I'll put a poll on CampusWare for a different time. So you answer that so that I know whether so that way I can set a time for office hour every week.
Thank you, Professor.
Let me see in chat window there is no questions. Again, this is not the end. You should ask question on YouTube video below that if you have any, or on CampusWare related to lecture materials. But read those chapters because those will be helpful for you for quiz. As I said, I asked those questions. All right, so he's on the recording now. I'm going to stop the sharing now.